Chapter 2, Analyzing Data, Section 3, Uncertainty in Data. Objectives for this chapter: define and compare accuracy and precision, describe the accuracy of experimental data using error and percent error, apply rules for significant figures to express uncertainty in measured and calculated values, review vocabulary, experiment, a set of controlled observations that test a hypothesis. New vocabulary: accuracy, precision, error, percent error, and significant figures. Main idea for this section: measurement contains uncertainties that affect how a result is presented. Go ahead and watch this movie.
Section B, Uncertainty in Measurement.
When we measure a physical property and we assign it a numerical value to that measurement, the numerical value is always an approximation. See, the accuracy of your measurement depends on the accuracy of your measurement instrument. So no measurement instrument is absolutely reliable.
The terms precision and accuracy are sticky. You may think they mean the same thing, but nope, not in science.
Precision measures the reproducibility of a result. In other words, if we take the same measurement 5 times, will we get the same answer all 5 times? If we do, our results are precise. Accuracy refers to how close our measurement is to the theoretical true value. When I say true value, I mean the value is determined by some brilliant chemist and listed in your textbook. If our measurement matches the theoretical true value, then the measurement is accurate.
So accuracy refers to how close a measured value is to an accepted value. Precision refers to how close a series of measurements are to one another. So if you look at these bullseyes, you can relate both of these terms to these bullseyes. You know when you're shooting a target, you want to get in the yellow, you want to get in the middle. And if you do, you are very accurate. If you hit multiple times in the same spot, but outside the yellow, you are very precise, but you're not very accurate. If you hit multiple times within the yellow, you are accurate and precise. If you hit in the white, this would be me, all over the place, you are not accurate or precise. Error is defined as the differences between an experimental value and an accepted value. Every time we do an experiment, we will have an accepted value, and we will compare the value you get to the accepted value. And how we do that is you take the experimental value, which is what you're going to get, minus the accepted value. We always put it in a percent error. You want your percent error to be as small as possible. So you want the absolute value of your error divided by the accepted value times 100%. Significant figures. This term has come up a couple times in the lectures here. Remember that the precision is only as good as the tool you're using. So significant figures include all known digits plus one estimated value. Okay, so if you're using this ruler here in centimeters, you know the 5 is a known value. You know that the 0.2 is a known value, but after that we can only guess. This is going to be 0.03, so we have 2 known values and 1 estimated. So we know our answer is going to be 5.23. Rules for significant figures. Non-zero numbers are always significant. So here you would have a total of 3 significant figures. Zeros between non-zero numbers are always significant. So in this number we have 3 significant digits. Rule 3, all final zeros to the right of the decimal are significant. Okay, so we have total of 3 in this number. Placeholders are not significant. To get rid of those placeholders, we need to put our numbers in scientific notation like we had talked about. Okay, so this would be 2.5, 2.5, 3 times 10 to the second. Okay, so there's only 3 in this number, and there's also 3 significant digits in this number. Now, counting numbers and defined constants have an infinite number of significant digits. Okay, so we have 6 molecules. Now, there is no decimal point here, so there is an unlimited and infinite number of significant digits. Okay, when you round numbers, remember, when you're using calculators, the calculators aren't aware of the actual problem. The answers should have no more significant figures than the original data with the fewest figures. Okay, so you need to go back to the original problem and calculate the significant figures. And your answer should be the same number of significant digits as the lowest in the problem. Okay, rules for rounding. Okay, I'm going to let you read through these. Okay, in addition and subtraction, round numbers so all numbers have the same number of digits to the right of the decimal. When you're multiplying and dividing, round the numbers to the same number of significant figures as the original measurement with the fewest significant figures. So we need to be really good at determining how many significant digits it has. Okay, when you use a measuring tool, it is used to determine the quantity, such as your height, weight, number. Okay, these are measured values. This is just review. Okay, exact numbers are obtained by measuring, counting, and definition. Measured numbers are obtained by measuring, counting, and definition. Exact numbers are contained by those two things. Okay, classify each of the following as exact or measured numbers. Okay, significant figures in calculations. The numbers reported in a measurement are limited to the measuring tool, as we've said before. Significant figures in a measurement include the known digits plus 1 estimated. Okay, calculate how many sig figs there are here. More practice. Okay, a calculated answer cannot be more precise than the measuring tool. A calculated answer must match the least precise measurement. Significant figures are needed for final answers from adding or subtracting, multiplying, and dividing. The answer has the same number of decimal places as the measurement with the fewest decimal places. Okay, do some practice here. Okay, rounding to the calculated answer until you have the same number of significant figures as the measurement with the fewest significant figures. Okay, do some practice again. Oops. Okay, determine the number of significant figures in the following. And I gave you the answer right away. One more. A substance that has an accepted density of 2.00 grams per liter. You measured your density as 1.8 grams per liter. What is your percent error? There you go. 10% error is pretty good.